Hello everyone, I'm Sergey. In this video, I will introduce a paper titled Polaritonic Fourier crystal. The concept of Polaritonic Fourier crystal was developed to address a problem of polaritonic dispersion engineering in thin van der Waals crystals. Polaritons are quasi-particles born out of coupling between free space photons and collective oscillations of charges in the material. Specifically, the low-dimensional polaritons in thin van der Waals crystals are strongly confined and thus are able to provide strong light-matter interaction. At the same time, their evanescent fields penetrate beyond the material boundaries and are exposed to external manipulation and probing. The scattering-type scanning near-field optical microscope, or SNOM in short, is often used to study the low-dimensional polaritons. In SNOM, a sharp tip of the atomic force microscope couples near and far fields via inelastic scattering. The scattered near field is analyzed by the interferometer, so that SNOM provides near-field amplitude and phase information in the output. However, polaritons are inherently lossy. Therefore, the realization of a polaritonic Fourier crystal based on low-dimensional polaritons is not an easy task. Van der Waals crystals have been shown to support various types of polaritons in a broad spectral range. In this work, we focus on mid-infrared frequencies where 2D semimetals support plasmon polaritons and polar dielectrics support phonon polaritons. Plasmon polaritons can be relatively easily manipulated by external doping of 2D semimetal, as usually done with graphene. However, the dispersion of phonopolaritons is strictly defined by lattice phonons, which are unavailable for external manipulation. So far, several methods to manipulate dispersion of mid-infrared phonopolaritons have been suggested. The most straightforward approach is to leverage the dependency of the dispersion on the refractive index of the substrate. For example, momentum of phonopolaritons in hexagonal boron nitride approximately doubles when HBN is on gold compared to silicon dioxide. Then, one can create a polaritonic crystal by periodically patterning the van der Waals crystal or the substrate. In this case, phonopolaritons may form collective block modes with non-trivial dispersion. In case of biaxial crystals, which support in-plane anisotropic phonopolaritons, their stacking and twisting leads to hybridization of modes between the layers. These hybrid modes have highly tunable dispersion, which depends on the twisting angle, as demonstrated here for the alpha phase molybdenum trioxide. Finally, topological edge states in artificially created topological boundaries also provide means to engineer dispersion of phonon polaritons. In previous works, we studied phonon polaritons in HPN alpha Mo3 placed on monocrystalline gold flakes. Both studies revealed that the lifetime of phonon polaritons screened by gold is similar to the lifetime in suspended material, while their momentum is significantly higher, thus increasing the number of optical oscillations in propagating polaritons. Furthermore, gold is a really good substrate for near-field imaging at mid-infrared frequencies, as it behaves as a lossless mirror. This significantly increases the signal-to-noise ratio in SNOM when polaritonic material is probed on gold substrate. If flat gold is such a good substrate for phonon polaritons, then how about using a corrugated gold substrate? Corrugated metallic mirrors have been used to create optical Fourier surfaces. Optical response of such a Fourier surface can be engineered to contain only specific harmonics in far field. We leverage this feature of Fourier surfaces to develop a concept of polaritonic Fourier crystal. Polaritonic Fourier crystal is based on a harmonically corrugated isopolymer film covered with thin gold layer. Such a corrugated gold mirror serves as a substrate for pristine polaritonic waveguide, in this case HBN crystal. As phonon polaritons propagate along the waveguide, their momentum experiences harmonic modulation due to varying distance between the HPN and the gold mirror. Most importantly, the high-order polaritonic modes M1 and M2 experience weaker modulation compared to the first-order mode M0. This is because their fields are more confined within the HPN and thus less affected by gold screening. Furthermore, this structure doesn't have any sharp material edges. Therefore, propagating phonon polaritons experience practically no scattering. In the absence of scattering, modes of different orders do not have mechanism to couple to each other, so that the optical response of the Fourier crystal is dominated by the lowest energy first-order mode, the one which experiences the strongest momentum modulation. The wafer-scale isopolymeric Fourier surfaces were created by holographic inscription method in the group of Professor Singwoo Lee at Korea University by PhD candidate Youngjun Lim. Thin gold film was deposited by vacuum deposition, followed by transfer of exfoliated HBN flake of desired thickness. Also, I would like to thank PhD candidate Jakob Hayden, who assisted in sample preparation. Here is the microscope image of the completed sample of Polaritonic Fourier crystal, a 106 nanometer thick HBN flake on top of the harmonically corrugated gold mirror with corrugation period of 485 nanometers. First of all, I would like to note that even a 106 nanometer thick flake remains flat over the 5 times larger corrugation period. This can be seen in the AFM scan across the HBN edge shown here. The near-field images measured far from the HBN edge to preserve an effectively infinite Fourier crystal configuration are shown here. Both amplitude and phase of the near field are significantly different at different frequencies within the upper Australian band of the HBN. This means that phonon polaritons experience very different propagation regime in the Fourier crystal depending on their momentum. To better understand the optical response of the Fourier crystal, we numerically calculated the band structure of phonon polariton block modes. As I mentioned earlier, the optical response is dominated by the first order mode, while higher order modes are suppressed. This is especially evident when compared with the band diagram of block modes in a conventionally patterned binary photonic crystal. In this case, sharp gold edges provide mechanism for intermode scattering. Thus, multiple high-order mode branches are clearly visible in the dispersion. The presence of numerous high-order modes in conventionally patterned polaritonic crystals has been leveraged in so-called polaritonic hypercrystals, which harness the much larger momentum of these higher-order modes. Although the band structure provides better understanding, the interpretation of near-field images requires analysis of individual block modes. Our colleagues Kirill Voronin and Alexei Nikitin developed a theoretical model that allows calculation of the band diagram for individual modes and full-wave simulation of their near-field response in SNOM model. Here is the band diagram for the first and second order block modes in the Fourier crystal, where HBN is approximated as a 2D conductivity sheet. These results correlate well with the full-wave simulations and reveal the presence of a wide bandgap in the dispersion of the first order block mode, even though we use the naturally abundant, relatively lossy HBN. This slide summarizes the hyperspectral near-field images measured far from HBN edges, showing both amplitude and phase along the 5 corrugation periods at different frequencies within the upper Australian band of HBN. On the left, there are simulated near-field maps for the first and second order block modes calculated within the 2D HBN approximation. The middle images show the calculated near-field map in a 106 nanometer thick HBN. Finally, on the right, there is an experimental data. The measured hyperspectral near-field maps show the characteristic pattern of the first order mode in both amplitude and phase. This is in perfect agreement with theoretical expectations, as only the first order mode is strongly modulated and the higher order modes are suppressed due to the absence of scattering. However, it is difficult to observe the predicted existence of the first order mode's bandgap in the near-field images above quasi-infinite structure where polaritonic fringes are not visible. Therefore, we also did near-field imaging of the HBN edge. Here is the microscope image of the HBN edge, which is deliberately oriented at some angle to the reciprocal lattice vector. Near-field images of the edge reveal a very interesting trend. Within the frequencies of the expected M0 bandgap, the bright near-field maxima are aligned with the peaks of the underlying gold surface, shown here as dashed lines, where the air gap between HBN and gold is 0. However, when frequency is outside of the expected bandgap, near-field maxima are observed where the air gap is the largest. Most importantly, Fourier spectra of the near-field images reveal the presence of the edge-launch polariton mode, indicated by the yellow arrow and illustrated here by the yellow wave, but only when the first-order block mode cannot be excited. The signal from the edge-launch mode disappears at the frequencies outside the bandgap. Both observations suggest the presence of the bandgap of the first-order block mode, which dominates the near-field response only at the frequencies where it is allowed to propagate. When the block mode is not allowed, the high-energy edge-launch mode comes to existence, and the near field is dominated just by the proximity of the gold to the sample surface. For further details on this work, please refer to the open access manuscript or contact the corresponding authors.